If you worrying about being late for a cross-city date, interstellar travel might drive you to utter despair. A round trip to the nearest star at light speed would see 9 full years pass on Earth by your return. Friends might even forget your name, but the universe has quietly tucked away a cheat card. The wormhole. It's like a built-in portal of space-time, allowing humans to leap across light years in an instant, provided you can survive the passage. The outcome of humanity's first man-wormhole experiment was the spacecraft vanished into the portal, only to be spat out 500 years later. Its crew long turned into statues frozen in time. Is this a shortcut to the starry ocean, or a dangerous fairy tale written into the cosmos? Welcome to Wormholes, the journey that may have no return. Those who have traversed a wormhole know that in interstellar travel, light speed is snail slow before a wormhole. But where do wormholes come from? Where should we look? And could they ever be realized? Imagine, in the not-too-distant future, humanity finally cracks open the door to interstellar travel, and it all begins with a simple test. One end of the wormhole lies in lunar orbit. The other extends to an empty patch of space near Neptune. There, a grand welcome party stands ready. Humanity once expended immense effort and resources to reach deep into the microscopic scales of quantum foam and capture a wormhole. After all, general relativity had long predicted their existence, and now it finally becomes reality. With this technology, humanity can at last touch the dream of interstellar travel. After final calibrations and fine-tuning, the spacecraft and its brave crew glide into the wormhole's throat, smoothly passing the spherical entrance on this side. Observers watch the craft recede into the distance as it seems to move effortlessly toward its destination. For 0.5 billion kilometers away, its outline slowly shrinks. On the other side, the welcome team also sees the craft approaching, its image growing larger with each passing second. Celebrations begin. Previous and manned probes took about 30 minutes to complete the journey. This manned craft appears to follow the same trajectory. Yet disaster strikes. Unease and whispers spread through the crowd. The craft seems to be slowing, then comes to a complete halt. It appears frozen in the amber of space-time. 30 minutes pass. The craft does not emerge. Days, weeks, months go by. Over time, precision telescopes at both ends finally confirm the craft is still moving, but at a speed almost imperceptible. Debates on what to do grow heated. Send a rescue mission or shut down the wormhole generator. Every choice seems to lead to the same tragic end. The delicate balance maintained by the exotic forces stabilizing the wormhole, once broken, would tear the craft and crew into cosmic dust. The only safe choice is to wait, and so they wait. After a long wait of 500 years, the wreckage of the craft is finally slowly spat out from the wormhole's other end. Its overall structure remains, but it is almost entirely disabled after centuries of exposure to the harsh environment inside the wormhole. Only a broken shell is left. The crew perished long ago. Their life support systems were never designed for such an extended voyage. Their remains, still strapped into the command chairs, resemble a set of frozen sculptures. Eventually, the wormhole is shut down, clearly humanity miscalculated. The predictions of general relativity alone were not enough. They thought they had unraveled all the intricate puzzles of gravity intertwined with quantum mechanics. But deep in the cosmos clearly lie rules they have yet to understand. Gazing up at the distant stars, humanity never felt so alone. Wormholes are complex. They were born in the equations of general relativity, their concept nearly as old as the theory itself. But unfortunately, for those test pilots headed to Neptune, relativity is like a cold machine. It only tells you how gravity would behave in various scenarios, never caring whether the universe actually allows those scenarios to happen. So what exactly does it take to build a wormhole? Which physical mechanisms hold the door open, and which slam it shut would it truly carry us to the distant stars of our dreams, or lead to premature death? Black holes and white holes, in the eyes of critics, it was obscure, sprawling, absurd, but to Edgar Allan Poe himself, this was his life's greatest work. It was 1848. Just a year before his mysterious death. The success of The Raven finally gave him some financial breathing room, and he used that margin to create what he considered his masterpiece. He called it the one great purpose of my literary life. The title was simple, Eureka. The book was vast, 40,000 words spanning life, death, science, spirituality, and ethics. But today, it is far less known than Poe's poetry, indeed. Even looking back nearly 2 centuries later, it is still regarded as obscure, sprawling, and absurd. Yet within its tangled arguments, certain statements shine with a chilling prescience. About 2/3 through, as Poe's thoughts wandered through the immensity of interstellar space, estimates of light speed, and the void between celestial bodies, he penned an oracle-like assertion. Space and duration are one. To Poe, space and time were the same thing. Nearly a century later, Albert Einstein, conducting his research, had no idea he was, in a sense, reshaping the ideas of a long-dead New England poet. But that is exactly what he ended up doing. It was 1905, the famous miracle year in physics history. In that single year, Einstein published 5 papers, each enough to overturn our understanding of reality. Each pioneered a new branch of physics. One of them, perhaps the most far-reaching, explored the relationship between motion and energy. It was in this paper that Einstein laid out his special theory of relativity, showing that measurements of length and time are relative, while physical laws themselves are the bedrock of the cosmos. Yet Einstein's former teacher, Hermann Minkowski, felt his student hadn't yet grasped the heart of the matter. Soon after, Minkowski provided an intuitive geometric formulation for Einstein's theory, presenting the universe as a four-dimensional object. Unlike Poe's idea, however, this new concept of space-time didn't mean space and time were identical, but different facets of a single unified entity. Einstein once again drew nourishment from his teacher and quickly adopted this new idea, using it to make an even greater leap within human imagination. In 1915, armed with a full understanding of space-time, Einstein released general relativity upon an unprepared world. In the language of general relativity, space-time is no longer a static stage, but a dynamic entity that responds to the presence of matter and energy. It bends and warps under matter's influence, and in turn, the curvature of space-time guides matter's motion. Years later, the renowned physicist John Wheeler summarized it all poetically. Matter tells space how to curve. Space tells matter how to move. In fact, right now, this is happening all around you and inside you. Gravitational ripples called gravitational waves, generated by distant cosmic catastrophes, constantly wash over Earth. As they pass, they distort space. If you could measure down to nuclear scales, you would feel yourself gently stretched and squeezed by these passing waves, much like Poe's work. General relativity itself is elegant, captivating, yet at times terrifyingly complex and bewildering. This is because it isn't merely a simple physical theory. It's more like an unrelenting machine. You input a setup, say a particular arrangement of matter, then feed it into relativity's equations, and it spits out an answer, a prediction of how that matter will move. Under its own gravitational influence, general relativity never tells you whether such an arrangement truly exists. Judging what is possible and what is impossible is up to you. This trait of computing without regard for reality isn't rare in physics. The Newtonian law of universal gravitation it replaced was the same. Tell Newton your matter arrangement, and the equations tell you how the system will behave. In principle, for example, you could calculate the gravity produced by a solid metal rod 10,000 light years long. But as for whether such a rod exists in the universe, Newton's theory remained silent. Yet what makes things more complicated is that, unlike Newton's earlier law, general relativity isn't a simple equation teachable in high school. It is a set of 10 intertwined four-dimensional nonlinear equations, so complex that Einstein himself only found approximate solutions. In fact, in a sense, nearly half a century passed before anyone began taking general relativity truly seriously. The physics community knew it was correct and useful, but it was so difficult to handle that pioneering physicist J.J. Thomson once admitted helplessly, "I must confess that no one has yet succeeded in stating in clear language just what Einstein's theory is." Nevertheless, exploration never ceased. Shortly after Einstein proposed relativity, Karl Schwarzschild, in the trenches of World War I, found a solution for the simplest matter arrangement, a lone sphere placed in the universe. In this case, Schwarzschild used relativity's machine, inputting a model resembling the solar system, and obtained a solution describing the strength of gravity around the sun. Although this solution aimed to model the solar system, it also gave birth to a terrifying possibility. The idea was, if this sphere of matter were compressed below a certain limit, it would continue collapsing. Its own gravity would grow so strong that it would become a point of infinite density, surrounded by a one-way membrane, the event horizon. Here, general relativity's machine had done its job. It gave an answer. Judging whether this answer was reality or fantasy became the task of physicists. Most at the time dismissed the idea. Indeed, Einstein himself rejected it. In a 1939 paper, He insisted no object could possibly shrink to the point where gravity overwhelmed all other forces, because that would require its constituent particles to reach light speed. He believed celestial bodies, then called frozen stars, simply could not exist in the universe, yet across the ocean. Another physics giant, Robert Oppenheimer, reached the opposite conclusion just months after Einstein's paper. Working with his student Hartland Snyder, he had just calculated the maximum possible mass of a neutron star and wondered what would happen if a star exceeded that limit. Their research showed that once other known physics was incorporated, black hole formation was not only possible, but inevitable. They found, indeed, no force could stop the infinite gravitational collapse of a sufficiently massive star. From there, general relativity's machine would tell you exactly what happens next, their paper stated. The star thus tends to close itself off from any communication with a distant observer. Only its gravitational field persists. Yet on the very day they published, Germany invaded Poland. Their findings were buried in the smoke of war, forgotten for decades. Oppenheimer himself was swept into the Manhattan Project and its ensuing political whirlwind, never returning to the mysteries of astrophysics. Nevertheless, over time, the existence of black holes became indisputable. But the story didn't end there. Did relativity's machine predict only this, or was there more? While Oppenheimer served the U.S. government, behind the Iron Curtain, Soviet astronomer Igor Novikov glimpsed in the same equations the hidden twin of the black hole in time's mirror, the white hole. Could they also exist in the universe in that special era? Being a physicist was tricky work. Still, he had enough freedom to pursue some obviously non-traditional lines of inquiry. His great insight in 1964 stemmed from a simple realization about gravity. Imagine we film you throwing a ball into the air and catching it, but we frame the shot so you can't see your hands, only the ball rising and falling. If we play the video backwards, would you notice any difference? Forward and reverse would look identical. Relativity's mathematics is similar. They don't know whether a process goes forward or backward in time. Gravity theories, including general relativity, don't care about time's direction, and black holes are a specific solution of general relativity. In 1964, Novikov realized the equations for black holes could run in reverse. They could expand rather than collapse. They could forever eject particles instead of forever capturing them. It could be not a black hole, but a white hole. Novikov proposed the idea to explain mysterious bright sources appearing in astronomical surveys. But as he was behind the Soviet Iron Curtain, his work was largely ignored by Western scientists. White holes are indeed strange beasts, perhaps even stranger than black holes. Their centers still hold a singularity, but they are surrounded by the opposite of an event horizon, an anti-horizon. They still have mass, so you'd still be gravitationally attracted to them, but you could never enter. The anti-horizon forbids anything from entering the white hole's interior, just as a black hole's event horizon forbids anything from escaping outward. Yet, if you found yourself inside a white hole at its formation, you wouldn't stay there long. You'd find yourself hurled outward at faster than light speeds, like an irresistible torrent. until you exited the white hole. White holes would keep spewing matter and radiation until completely emptied, leaving only a naked singularity and its anti-horizon. If that weren't strange enough, unlike black holes, which can form in the future from collapsing massive stars, white holes could only have formed in the past and be erupting outward now. They are the precise time mirror of black holes. Later, physicists favored another explanation for those distant bright sources, energy released by matter falling into black holes. But as late as 2014, Novikov still believed some of those bright sources could be white holes, formed in the early universe through some exotic mechanism, and still shining today, though most physicists dismiss the possibility of white holes, as their predecessors once did for black holes. A few remained intrigued. Roger Penrose, who later won a Nobel for his work on black holes, noted Novikov's work and realized it might be the ingredient needed to explain another strange solution in general relativity, a tunnel connecting one universe to another. But ultimately, it was Penrose's friend and colleague John Wheeler who gave these tunnels their modern name, wormholes. He realized white holes and black holes could be joined. In fact, this knot had been found decades earlier by a relatively unknown assistant of Einstein himself. With this solution, Wheeler realized a small branch of relativity might be developed into a method for leaping across light years and traveling among the stars. He only needed to see whether what general relativity's machine spat out was a stroke of genius or a mad delusion. They were a dozen men and women from Europe and America who would gain deep insight into nature's inner workings, conceive elegant mathematical proofs, and conjure results from groundbreaking experiments. In short, they were all geniuses, but they all faced the same inescapable fate, living in Einstein's enormous shadow. Like swimming beside Michael Phelps, you could never be the champion in the pool. Einstein's collaborators had no hope of claiming the title of smartest person in the room, yet even so, Einstein himself never looked down on or disrespected them. On the contrary, he often turned to them for help of his friend Michel Basso. Einstein called him the best sounding board in Europe. His first wife, Mileva Merrick, was also a frequent sounding board collaborator and conversational partner for his early ideas. And among these geniuses, one name was destined to be closely tied to Einstein's, Dathan Rosen. He first met Einstein in 1934 at the Institute for Advanced Study in Princeton. Rosen was bright, capable, hardworking. He even proposed a broadly correct model of the atomic nucleus before the neutron was discovered. But had it not been for his collaboration with Einstein, his name would unlikely be mentioned so often today. Rosen spent months at Princeton before mustering the courage to visit the legendary physicist. When he finally did, timidly knocking on the genius's door, Einstein immediately put the young Rosen at ease. As Rosen himself recalled years later, I told him about my work. He seemed interested and asked many questions. Rosen was particularly interested in Einstein's doom efforts to unify gravity with electromagnetism, which likely strengthened their bond. It was during this collaboration that Rosen extracted from relativity's machine, an extraordinary new result. Einstein was then particularly frustrated by the appearance of singularities in the theory, and equally frustrated by the tendency to treat subatomic particles as having no size. He sought a way to eliminate both difficulties, and Rosen found a way. Rosen and Einstein imagined tracking the path of a line falling into a black hole and crossing the event horizon. Normally, we'd think that's the end, cut off from the universe forever, meeting final fate at the central singularity. But Rosen proposed a startling conjecture. What if the line could keep going? What geometric construct would let it avoid the singularity altogether? It was a captivating question, and Rosen happened to have a machine to answer it. General relativity, what space-time structure would allow such a path to exist? Rosen found that if you followed this path, you'd eventually return to the universe, but not where you started. This path would form a bridge between two different regions of the universe. This meant the universe wasn't simply singly connected. Multiple paths, even shortcuts, could exist in space-time. These bridges would continuously connect one region of the universe to another. No singularity, no breakdown of general relativity, just a path into a black hole and out the other side. To complete their theory, Rosen and Einstein added the electromagnetic fields to the calculations, hoping this singularity-free solution would also explain the emergence and properties of subatomic particles. Unfortunately, this attempt failed, as it led to a prediction that particles must be massless. Thus, these structures, later called Einstein-Rosen bridges, sank into relative obscurity. Another 20 years passed before American physicist John Archibald Wheeler picked up Nathan Rosen's obscure idea and gave these bridges a new name: wormholes. Clearly, Wheeler had been fascinated since childhood by questions that challenged convention. His mother recalled, when he was 4, playing in the bathtub, he suddenly went still, looked up at her, and asked, "What happens when we get to the end of everything?" Indeed, he never abandoned that childhood curiosity. It was this boundless inquisitiveness that let him explore questions others dared not tread, including Rosen and Einstein's mysterious bridges. For it was he who realized these bridges might provide a mechanism for interstellar travel. These bridges weren't mere mathematical constructs. They were space-time tunnels that could be shortened. In principle, you could reach distant stars without lifting a finger. But almost immediately after this realization, he saw that any traveler attempting to cross a wormhole would be instantly shredded into dust by gravity. Rosen and Einstein had imagined entering a black hole, yet avoiding the final fate of the singularity, emerging unscathed elsewhere. In that sense, the other end of the bridge they envisioned was a white hole, the mirror of a black hole. Wheeler was among the few Western scientists aware of Novikov's work in the Soviet Union. He realized that in general relativity's mathematics, nothing prevents such an eternal black hole from existing. A space-time tunnel with a black hole at one end and a white hole at the other. Was the problem solved then? Far from it, for such a wormhole had two fatal flaws. First, general relativity isn't all of physics. There's more in the universe than pure gravity. Second, just because a wormhole can be created doesn't mean it can persist for decades. Physicists wrestled with the concept of black holes and their thorny implications, but ultimately evidence won. Now, all physicists accept their reality. For white holes, however, that's not the case. White holes are black holes run backwards in time, possible in general relativity, simply because general relativity itself doesn't care about time's direction. But we care, other theories of physics care. For instance, the rock-solid laws of thermodynamics care about time's direction and the increase of entropy. You can have matter collapse to form a black hole. Entropy increases. That's allowed in the universe. But you can't have matter expand to form a white hole. That would require decreasing entropy, which is strictly forbidden. In the known universe, no mechanism can create a white hole using existing matter and physics. When a star collapses, immense energies and forces prevent a white hole from forming, as if pinching off that part of the Einstein-Rosen bridge, leaving only the black hole, perhaps, in the early universe filled with exotic and unknown physics. Some exotic process could create white holes and leave them as relics. In our present universe, would that be the answer? Unfortunately, no. Even if you could somehow create a white hole through some mysterious mechanism in the Big Bang or in a lab, it couldn't last. A white hole still has positive mass and a singularity at its center. If you encountered it, you'd still be attracted by its enormous gravity, but you could never enter. Its anti-horizon is absolutely exclusive. It permits nothing to enter, thus you'd be trapped, drawn ever closer by gravity, yet never crossing the anti-horizon. The system's energy would keep rising, eventually running away. Simply put, it would explode. Thus no known mechanism can create white holes, and once formed, no known mechanism can keep them stable. For these reasons, physicists rightly distrust that white holes exist in nature. Unlike their twin siblings, black holes, white holes are doomed to remain mere products of mathematical imagination in Einstein's relativity. But dreamers like Wheeler and Novikov weren't bound by a single theory. After all, we've updated our understanding of gravity before. We also expect, or at least hope, to update general relativity in the future. So even though our current physics knowledge forbids white holes, perhaps a more subtle approach could make them possible. Perhaps wormholes are possible, but unfortunately, even if you could perform some miraculous technological feat, creating a white hole and keeping it open as the exit of an Einstein-Rosen bridge, we find you should still never enter it. The problem is, the space-time described by Einstein and Rosen, what we now call an eternal black hole, is static, a simple description of a geometric structure frozen forever in time. But as John Wheeler asked his mother at age 4, what happens when you get to the end of everything? If you created this wormhole and actually tried to traverse it, what would happen? The interior of a wormhole is no pleasant place. They aren't serene tunnels through space-time, but regions filled with intense, greedy gravity that not only pulls inward, but tears apart. Indeed, every time the moon orbits Earth, It gently tries to rip Earth apart. We call that tides. An object falling into a black hole gets stretched and squeezed before being shredded into atoms, a process physicists call spaghettification. And the gravity inside a wormhole is likewise so strong, so violent, so twisted, that if a wormhole forms, it would be forced to stretch along its length and pinch at its middle like an overstretched rubber band. The wormhole would tear itself apart in a frenzy of gravitational energy. In fact, Wheeler found this destruction occurs faster than light speed. Nothing, not even light, could safely cross the wormhole's throat and emerge from the other end before the tunnel destroys itself. Perhaps you could catch a fleeting glimpse of your destination. Light from both ends could fall in, letting you see the universe of both your departure and arrival points. If someone entered from the other end, you might meet inside the wormhole tunnel, sharing stories and experiences from across the cosmos. Then the wormhole would collapse, leaving you inside the black hole, its singularity your only possible destination. You would die. Thus, after Wheeler pronounced wormholes terminally doomed, most physicists accepted they were literal dead ends. Clearly, once you cross a black hole's event horizon, whether it's a standalone entity or the entrance to a wormhole, you cannot escape. Not even Einstein and Rosen's clever geometry could save you, but predictably. This wasn't the end of the story. Decades later, a third generation of physicists would take up the challenge posed by Einstein, Rosen, and Wheeler, and indeed, it was a student of Wheeler himself who found a way to create stable, traversable wormholes. He just needed a little help from science fiction. Looking for rigorous physics in sci-fi movies, Star Wars isn't the place. Laser beams slower than real-life bullets. Moon-sized space stations defying their own gravity. Weapons capable of destroying entire planets. And of course, ships that travel faster than light with the flick of a switch. While Star Wars is superb entertainment, its footing in known physics isn't solid, but sometimes a writer or director wants their work closer to our modern understanding of the universe. Christopher Nolan's film Interstellar is an example. Interstellar's world is fairly realistic. A crop-blighting disease hints at the ravages of climate change, and NASA, fallen from glory, attempts to mount a mission to explore a mysterious object appearing in the outer solar system. Though Nolan took such care building a realistic world, he still wanted his crew of astronauts to cross vast distances in short time, so he brought in a general relativity expert, Nobel laureate Kip Thorne, for ideas to Thorne. Faster than light travel was absolutely impossible, but instead of rejecting Nolan outright, he compromised, offering a possible solution. The physicist suggested using a wormhole, a shortcut through space-time, a stable, traversable wormhole. This certainly had a ring of fantastical tech, but wasn't entirely ruled out by modern physics. Indeed, if anyone would know, it would be Thorne, because back in the 1980s, while helping another famous friend, the legendary science communicator Carl Sagan, craft his sci-fi tale, Thorne himself had realized this in Sagan's novel Contact. Humanity receives instructions on how to build a wormhole. A team traverses it in a dialogue. Sagan wanted his characters to ponder how this could be possible, but he didn't know what they should say, so, like Nolan later, he turned to Thorne. By then, of course, wormholes were known to be catastrophically unstable, so Thorne and his collaborator figured out a way to stabilize them. This idea wasn't initially a serious theoretical physics exploration. In fact, the paper he co-authored with Michael Morris in 1988 on the topic was titled Wormholes in Spacetime and Their Use for Interstellar Travel, with the subtitle, A Tool for Teaching General Relativity. Clearly, the wormholes of Rosen, Einstein, and Wheeler simply wouldn't work. White holes, even if creatable, were fundamentally unstable, and their bridges with black holes were only temporary. So to make wormholes useful, in Thorne's terminology, traversable, you had to solve the problems simultaneously. First, you must place the wormhole's entrance outside the event horizon of a black hole. That's the only way to avoid destruction at the singularity. Second, you must stabilize the passage itself. Apply some kind of pressure on the tunnel walls to keep them from collapsing instantly. Thorne found a simple trick within the universe that could solve both problems within general relativity's equations. Usually, most physicists use general relativity one way. Given an arrangement of matter and energy, they use the equations to compute the resulting space-time curvature. Then you compute gravity and predict the system's future behavior. But Thorne ran the equations backwards. He started with a specific space-time structure, a wormhole bridge connecting to regions of the universe, and asked the equations what matter-energy configuration would be needed to keep this tunnel stable. As always, relativity's machined faithfully, ignorant of what is possible or impossible in the real world, spat out an answer: negative mass. Note: this is not antimatter. Antimatter has positive mass, just opposite charge. This is truly negative mass. Like a football weighing 500 grams or you buying 2 kilograms of meat from the store, negative mass doesn't attract, it pushes away and repels. If you shaped negative mass into a shell, the surrounding space-time would react by pushing itself apart. This pressure could blow the wormhole's entrance outside the event horizon, letting you enter the tunnel without being swallowed by the black hole at its core. Likewise, negative mass pressure could keep the tunnel open, resisting its natural tendency to self-destruct, and allow objects, light, particles, spacecraft to pass through. Thus, the key to a viable wormhole was revealed in relativity's cold mathematics. But there's a catch. Where do we find negative mass? Despite decades of searching and experimentation, physicists and astronomers have found no matter with negative mass. Such matter is called exotic matter, and even if it did exist, it would pose serious problems for our most basic, fundamental notions of momentum and energy. For example, exotic matter might react opposite to forces. If you kick a negative mass football, it would fly backward, not forward. If you drop it, it would fly upward into the sky. Exotic matter would break our understanding of momentum conservation, a cornerstone behind almost all modern physics theories. Of course, momentum conservation could be wrong or at least incomplete, but after centuries of scrutiny, It shows no weaknesses, no cracks in its ability to explain the universe's behavior. Thus, exotic matter seems a dead end. What Einstein showed us, matter and energy are two sides of the same coin. So if exotic matter can't be made and shaped into a wormhole, perhaps exotic energy could. And the origin of exotic energy began with an old-fashioned gunfight. It was just after World War II. The streets of Copenhagen turned into dusty main streets of the Old West. Cowboys in suits wielded simulated weapons in simulated duels. One participant was Hendrik Casimir, a young graduate student more interested in particle physics than mock gunfights. Overseeing this strange experiment was the father of quantum physics himself, Niels Bohr, stopwatch and notebook in hand. Casimir was in Copenhagen to study quantum mechanics, but Bohr had temporarily diverted from his main interest to indulge a hypothesis he'd created, today called the gunslinger effect. He believed automatic reactions were faster than intentional ones and wanted to test the idea. Willing or not, Casimir had to step away from his studies to play gunslinger. Perhaps when he returned to hardcore physics research, the image of fellow grad students staring each other down across a distance, fake guns holstered, stuck in his mind, letting him imagine tension and forces between two metal plates placed close together while studying quantum mechanics under Bohr. His calculations revealed an extraordinary property. With nothing between two metal plates, they would spontaneously move toward each other, as if pulled by a new, invisible force. But this wasn't some new force of nature. It was an effect of quantum mechanics. Quantum mechanics doesn't view the universe as filled with particles, but with fields occupying all space-time. Everywhere, these fields are filled with vibrations, constantly flickering between existence and nothingness. Sometimes these vibrations become more substantial and propagate. That's what we call particles. But most vibrations vanish before the wider universe notices. In fact, across the vast expanse of the cosmos, an infinite number of vibrations occur everywhere. Yet between two metal plates, these vibrations are restricted. Through careful calculation, Casimir proved the difference between vibrations outside and inside the plates produces a weak push, a force that draws the plates together, because the energy in the region between the plates is lower than the average energy of the vacuum. The Casimir effect, named after him, became humanity's first window into negative energy and reality, and a sufficiently concentrated negative energy could prop open a wormhole, stabilizing it and allowing traversal. Such a wormhole would be a spectacle utterly unlike anything observed in the cosmos. Its entrance would be a sphere, somewhat like a black hole's event horizon, meaning you could enter from any direction, but it would glow brilliantly, not with light from nearby stars, but light shining through from the far end of the universe. You could wave to a friend in the Andromeda galaxy, study its stellar composition, or travel there yourself. Traversing such a wormhole would be relatively easy, assuming the tunnel is properly stabilized with enough negative energy. You wouldn't experience extreme tidal distortions or incredible gravitational bending, though your view of the external universe would be highly warped due to the tunnel's unique geometry. you'd pass through unscathed, skipping dozens, hundreds, millions of light years with ease, at least in principle, because once again, things aren't as simple as they seem. We have physical laws like general relativity, but often the mathematics in these laws has a wider range than our physical universe. For instance, some solutions of relativity are allowed in our universe, like black holes, while others, like white holes, are not. To address this, over decades, physicists developed a set of rules to guide which solutions are allowed and which are not. These rules are called energy conditions. There are various energy conditions. Broadly, they tell us how energy can behave. For example, energy can't travel faster than light, just like matter. Another condition states local mass cannot be negative. Exotic matter is forbidden due to its momentum implications. Yet another says local gravity must always be attractive. The Casimir effect violates the weak energy condition . The rule that energy must always be positive. But of course, this holds only in the superlocal space between the plates. If you average over a larger volume, including the plates and surroundings, total energy is positive. The energy condition is satisfied again. Whether energy conditions can be violated on macroscopic scales is an open question in physics. They seem to hold on macroscopic scales, but then again, they are only guesses based on our experience with gravity. Exotic quantum phenomena like the Casimir effect could potentially be amplified by a sufficiently advanced civilization. In fact, quantum theory predicts the existence of countless, perhaps infinitely many wormholes. Those quantum fields constantly vibrating, flickering between existence and nothingness, generate an unseen sea of particles that disturb and disrupt space-time. At the tiniest scales, this is called quantum foam, a turning, fractured, irregular sea of space-time, on scales so tiny in time and space as to be undetectable. That foam contains innumerable submicroscopic wormholes. So perhaps, as Thorne mused in his 1988 paper, an advanced civilization could capture one such ultra-tiny wormhole from the quantum foam and carefully enlarge it to macroscopic size. Perhaps they could find a way to violate energy conditions on macroscopic scales, extending Casimir-like effects from tiny gaps between plates to lengths spanning intergalactic distances. Perhaps that civilization could use this technology to send a pair of brave crew members to distant stars. But a functioning wormhole, as enticing as it sounds, isn't merely a bridge to distant galaxies. It's also a tunnel to the past, breaking chronology. Now imagine you receive an invitation from the past. The venue, Cambridge University. If more precise coordinates are needed, the party is at 521,221, 7 for .7e. The party starts promptly at 12 o'clock UTC, June 28, 2009. Champagne will be served, and your host is none other than the famed astrophysicist Stephen Hawking. At that exact location, and more importantly, time, Hawking arrived at his reserved room. He had some champagne, then waited. He waited hours. No one showed up. He left. Only after the party ended did he distribute his invitations. It was a party for time travelers. No guests showed seemingly reasonable evidence that time travel is impossible. After all, who in the far future would refuse a chance to meet Stephen Hawking? But Hawking himself wasn't entirely discouraged. He said, "I hope copies of the invitation will survive in some form for thousands of years. Maybe someday, people living in the future will find the information and use a wormhole time machine to come back to my party, proving that time travel will be possible one day." So is he right? Could wormholes be the key to time travel? As far as we can observe, traveling back in time is impossible. Yet once again, relativity's machine seems to be causing trouble, for its equations allow it. Let's assume our physics knowledge advances from its current state. We discover a way to violate energy conditions and build a viable, traversable wormhole propped open by exotic matter or negative energy. You build your device, hopping between stars faster than light. Of course, this never happens locally. You'd never measure yourself moving faster than light. That conforms to relativity. But meanwhile, you could arrive before your departure message reaches the destination. Then you take one end of the wormhole and accelerate it to near light speed. Actually, where you take it isn't crucial. What matters is it's moving fast, according to special relativity. That end of the wormhole experiences time dilation. Its clock falls out of sync with the other end. So if you travel outside the wormhole, return to the unaccelerated end, then traverse the wormhole. As long as your travel time outside the wormhole is less than the time difference between the two ends, you could arrive before you left. A wormhole was never just a shortcut through space. It is inherently a tunnel through time. If the universe allows us to build wormholes, it automatically means it allows us to build time machines. But time travel opened so many paradoxes that most physicists consider this reason enough to deem wormholes impossible. But why can't we travel through time? Consider this example. You have a machine that creates wormholes. You can open a wormhole and you can close a wormhole. So you open a wormhole back to the past. Then you close the wormhole or detonate a bomb, utterly destroying the entire wormhole generator. But if the wormhole is closed or destroyed, how did you ever go back to close it in the first place? This is just one example of the countless paradoxes inherent in time travel. Thus, anyone delving deeply into wormholes must confront the difficulty of time travel and conceive solutions. Navigative, father of white holes, himself created the self-consistency principle. He argued maybe time travel is allowed, but only in specific circumstances where the past remains unchanged. For instance, you throw an asteroid into a wormhole entrance, but at the last moment before entry, another asteroid strikes, deflecting yours. It still flies into the wormhole, but on a different trajectory than you intended. This asteroid traverses the wormhole, emerging in its own past, only to collide with itself just before entering the wormhole. Thus, the universe's history stays consistent. The past wasn't altered. Some unknown mechanism prevents tampering with the past, but other physicists reject the idea of time travel altogether. In fact, in a 1992 paper, Stephen Hawking himself said, "It seems that there is a chronology protection agency which prevents the appearance of closed, time-like curves, and so makes the universe safe for historians. Hawking's asterisk chronology protection conjecture asterisk straightforwardly states, time travel is forbidden, so we shouldn't try to find a way to allow wormholes and time travel to exist. Rather, we should turn it around. Use the fact that time travel seems forbidden as a guide to constructing an improved quantum gravity theory. Yet the story isn't over, because perhaps wormholes aren't tunnels to the past, but bridges to entirely different universes. In the asterisk many worlds interpretation asterisk of quantum mechanics, championed by Hugh Everett, every quantum interaction leads to a branching multiverse. For example, if we perform an experiment with 50/50th outcomes, one U in one universe measures one result, while another U in another universe measures the other. This interpretation of quantum mechanics has many flaws, but hasn't been explicitly ruled out by any experiment. It opens the possibility that wormholes could let us travel to other branches of the infinitely expanding and splitting quantum multiverse. By this logic, perhaps in one universe among many worlds, party-goers from the future did arrive at Hawking's party in their universe. Hawking's party was always a success, while in ours it always failed. Hawking's chronology protection still holds, yet time travel remains allowed. Thus, the existence of wormholes in general relativity's equations opens a series of captivating, mind-bending possibilities. The ability to hop between stars, the ability to jump back into our own past. Perhaps wormholes are forbidden by some yet undiscovered law of gravity. Perhaps they are allowed but contain hidden flaws and traps. Or perhaps they are simply too slow. In 2019, a research team from Harvard and the Institute for Advanced Study found a way to conceive wormholes without exotic energy, but there was a catch. These wormholes would take far longer than expected. They used a gravity model not applicable to our universe, but focused on a space-time with only two spatial dimensions and one time dimension. Surprisingly, such a wormhole didn't need exotic matter to stabilize it. Gravity itself, in the extreme geometry of the wormhole tunnel, becomes repulsive. That alone could prop it open and allow passage. But analysis of the same geometry showed such a tunnel couldn't be used to hop across the universe faster than light. In fact, the path through the wormhole would be even slower and longer than staying in flat space. This wormhole was not only a poor way to cross the cosmos, it was worse than not building one at all. Admittedly, the researchers used a modified space-time structure to study this wormhole, one not identical to the physical universe, but it still raises an interesting, yet frustrating idea. Wormholes may well be possible, but they may also be useless. From Poe's poetic visions to Einstein's cold equations, from Wheeler's fatal traps to Thorne's sci-fi antidotes, to the ultimate paradox of time travel, the story of wormholes is filled with hope, despair, genius, insights, and the universe's relentless laws. Despite these recent findings on balance in our universe, most physicists' current consensus is wormholes are ultimately not allowed. but they can still serve as useful playgrounds to test new ideas in gravity and quantum mechanics. Studying physics in one of the most extreme configurations imaginable, using their strange behavior to probe not unknown regions of the cosmos, but corners of knowledge currently hidden from us. As Stephen Hawking reflected on the difficulty of understanding wormholes, time travel, and quantum gravity, God not only plays dice, he sometimes throws them where they cannot be seen. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries, and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.